Hi everyone. This video is going to continue with the same set of handouts that we worked on last class. It's the first of two videos. Both of them you're going to fill out along in the handouts and scan them in and post them for a quiz/classwork grade for this weekend. So we left off last class talking about the domain of rational functions. That was on the previous page. So here we're going to pick up and talk about how to find the different intercepts, or different asymptotes, for these rational functions. So for a vertical asymptote, we find that vertical asymptote, remember, they're related to the domain in that the vertical asymptotes are going to occur where the rational function is undefined, okay? But it has to be in simplest form. So to find a vertical asymptote, okay, the first thing you want to do is simplify, put the function in lowest form. And then see where it's undefined. And find the x values where it's undefined. And this is where your vertical asymptote will be. So remember, there's a difference between a vertical asymptote and a hole in the graph. So I'm going to put an example here that shows both. Okay, so let's say we have a function like this. F of x equals x squared minus 4 over x squared plus 3x plus 2. Okay, so we have that function right there. So we're really focusing on the denominator for the vertical asymptote to see where it's undefined. But we have to really put it in simplest form to see if there's any factors that cancel out. So if I were to factor the top of this, it would factor into x plus 2, x minus 2. And then the denominator will factor into x plus 2, x plus 1. Okay, so we see that these two factors right here would cancel out. Okay, so when I'm picking out my vertical asymptotes, I'm only looking at where this simplest form, where this reduced function is undefined. So I would have a vertical asymptote at, that was supposed to be my at sign, it came out a little messy, at x equals negative 1. Okay, that's where this is going to be equal to 0. So it's not to say that it doesn't matter. The fact that these canceled out, I still have to somehow show that, because that is saying that in the original function, I would not be able to plug in a negative 1 or a negative 2. In the reduced function, in the simplest form one, negative 1 is the only one that's undefined. But the way that other one plays into it is that this graph would have a hole at x equals negative 2. That was the spot where the original was undefined, okay, but that factor canceled out. So we call that a hole, or we also call it a removable discontinuity. I think we wrote that on the other page. Removable discontinuity. Sorry, I can't squeeze that in. Okay, so now we'll look at how to find the horizontal asymptotes. So these ones come from, there's actually 3 rules that we look at to figure out the horizontal asymptotes. So they don't come from where the denominator is equal to 0. These come from, a horizontal asymptote is when, if you look at the end behavior of these rationals, if you look at what's happening as x is going to infinity or negative infinity, what y value the graph is approaching. So what ends up happening, okay, so what we look at is the degree of the top versus the degree of the bottom. We compare those 2 degrees. So we've got 3 things that could happen. If we're comparing the 2 degrees, okay, the first thing that could happen is if the top degree, I'm just too lazy to write numerator, I'm writing top instead. If the top degree is less than the bottom degree. Okay, that's one thing could happen if we're comparing the 2 degrees. If that's the case, then there is a horizontal asymptote. Oops, let me fix that. Then there's a horizontal at y equals 0. So that's kind of an easy one because it's set. I don't have to do any more. It's always going to be at y equals 0 if the top degree is less than the bottom degree. Okay, so for example, let's say you had this function here. F of x equals 5x plus 3 over x squared minus 1. Okay, so let me just choose a different color here to go through the degrees. So the top polynomial right here would really be a degree 1 because it's linear, right? Because the highest degree is 1, and the bottom degree is a degree 2. Okay, so in this case, the top degree is less than the bottom degree, and this one would have a horizontal asymptote at y equals 0. Okay, so let's see what else could happen, right? So again, we're just comparing the degrees. So what if, the second scenario would be what if the degrees are the same? Okay, so if I won't be as lazy here. If the degree in the numerator is the same as the degree in the denominator. Okay, that could happen. And in that case, there's a horizontal asymptote is, okay, so this is, let me write it out first and I'll explain it. Okay, so it's always a y equals line because it's a horizontal asymptote, and it's the ratio of the leading coefficients. So I'll have a horizontal asymptote at the equation y equals whatever the ratio of the leading coefficients is. So let me give an example here. Okay, so let's say we had some function. Let's make it 2x squared minus 3. And then we'll make it 5x squared. I'm putting both of these in order, but keep in mind they don't have to be, right? And the leading coefficients are the coefficients of the highest degree term in there. So in this case, we have the top one being, I'm just in blue, I'm writing the degree. That's a degree 2, and that's a degree 2. So that's what I mean when I say the same degree. Okay, so for this one right here, my horizontal asymptote is going to be at y equals. So I look at my ratio of my leading coefficients, which in this case, I do have them in order, so they're right lined up with each other. But either one of these could be written, you know, the top or the bottom could be written in different order, and it has to be the ratio of whatever the leading coefficients are, the ones in front of the highest degree. So this would be at 2/5. Okay, so that really means that if you looked at the end behavior of this one, as x went off to infinity or off to negative infinity, the y values would approach 2/5 all the time. Okay, and then this last scenario, it's both hard and easy all at once, okay? In terms of a horizontal asymptote, it's easy, but you'll see what I mean. Okay, so the third scenario that it could be, right, we talked about if the degree on the top is smaller, if they're the same, and let's do this last one. If the degree in the top, getting lazy again, I'm really lazy, is greater than the degree in the bottom. I hope my handwriting in class when I'm on paper is better than this, but it is super hard to write with a stylus. If the degree in the top is greater than the degree in the bottom, then what's nice about it is there's no horizontal asymptote. There's no horizontal asymptote in this case. Okay, so that's the good part. But in that case, we will look for a slant, what we call a slant asymptote. It's called a slant or oblique asymptote. All right, so we're not going to do this one today. We're going to do it next class, but we look for that by dividing, by using long division, long or synthetic division. All right, so I'll show you an example of that next class. Let me just put an example, not of the slant, but let me just put an example of what it looks like for the degree in the top to be higher. All right, so let's say we had some function that was like a cubic on top, something like this. and then the bottom was anything less than a cubic, right? So it could be linear or quadratic on the bottom. So in that case, my degree on the top, right? My top degree would be degree 3. My bottom degree would be degree 2. So the top degree is higher. So that would have no horizontal asymptote, but we would look for a slant asymptote by doing the division out. So lastly, we will look at, I'm going to switch slides, and this will be the next page in that handout. So for today, all we're going to do is this first one. And then the next one we'll save for class next time. So let's look at this, and we're going to find a bunch of things. We're going to find the vertical asymptote. We're going to find a horizontal asymptote. Anything else that comes up, and we'll find intercepts in a second. So I'm going to leave a spot for something. Well, actually, I'll put what we're looking for is if there's any holes. If there's not, then that's fine. We're going to find a y-intercept, and we are going to find x-intercepts. And then we'll try to give a sketch. Okay. So when I'm trying to find my vertical asymptotes, the first thing I'm going to do before I really list any of that stuff is I'm going to see if anything can be factored and if anything can be put in simplest form. So let's see. The bottom's easy because that one factors into x plus 1, x minus 1. So the top one, when I look to factor that, before I jump into anything like AC method or anything like that, I'm actually going to just pull out a 2. I'm going to do that right above. And I'm going to write that as x squared. I'm pulling out a GCF of 2. And I get a 2 times x squared plus 2x minus 3. So when I factor that, all right, that's going to factor. That's an easy factoring. I get an x plus 3, x minus 1. So I notice that I do have 2 factors on the bottom, so I have potential to have 2 vertical asymptotes. But I would only have 2 vertical asymptotes if neither of those factors canceled with something in the top. Okay, remember, otherwise it's just a removable discontinuity. So these do cross out. So my simplified expression is really what's left over there, that 2 times x plus 3 times x plus 1. I have to make sure that I address that hole because there is a hole at x equals 1, but there's only a vertical asymptote at x equals negative 1. So if I were listing my domain, I would have to exclude both of those values. So actually, let me add that in the last thing. My domain would be, I could go from negative infinity all the way to negative 1, and then I could go from negative 1 to 1, and I could go from 1 to infinity. So that does take into account holes and vertical asymptotes. Okay, so let's try our horizontal asymptotes. So I can look at it in simplest form. It doesn't really matter which one because nothing really changed with it's still the same degree. So if I look at the original one or if I look at the simplified one, both of them, they have the same degree, which means this is going to follow rule 2 that we wrote on the other page. And so rule 2 says that it's going to be my leading coefficients. So in this case, it's going to be at y equals 2 over 1, which we'll write as just 2. Okay, so for my x-intercepts and my y-intercepts now, so my y-intercept, I'm just going to take and plug in a 0, everywhere I see an x. So for my y-intercepts, here, I'll come over here. My y-intercept, I'm just going to do the original one. I think it's actually easier. If I plug a 0 everywhere I see an x, all I have left is the negative 6 over the negative 1. So I get a 6. And then my x-intercepts, remember I'm going to plug a 0 in for the output. Now I think it's actually easier to use the simplified factored one. And for that, so if I were solving that equation, if I was trying to solve that for x, this is kind of a good start to solving rational equations. I'd multiply both sides by x plus 1 first. Right? And I get a 0 equals 2 times x plus 3. So the idea is with rationals, when I'm finding my x-intercepts, I'm actually only concerned with when the numerator equals 0, because that's when our whole function is going to be 0, when you have 0 over something. So the only thing that will make this work would be -3. Okay, if I looked at the original one, before I cross out the factors, I would say there's an x-intercept at -3 and at 1, except remember x is not allowed to be 1 because there's a hole there. So my only x-intercept here, my only x-intercept is at the point -3, 0. All right, so it's really good to be able to take all this information and draw yourself a picture. So I'm just going to end with that. So let me draw an axis. Okay, so let's see here. I think I have to go higher on my x-axis here. So you guys make a graph as I'm doing it. Okay. All right, so 0, 6. Actually, the easiest thing I think to add on my graph first is my asymptotes. So I have an asymptote at x equals -1. It just really helps form your graph. So this is always the first thing I do. And I have a y asymptote at 2. Because once you have these in, you can kind of see where the graph has to approach. So 0, 6 was my vertical intercept, which is right there. And -3, 0, right there, is my horizontal. So sometimes I have to find more points to fill in, but for what I'm doing here, I actually have everything I need. Because if you look at it right here, I know I have, whoops, sorry, I chose the wrong tool. I know that I have to approach both of these asymptotes and go through that point. So the only really way to do that is for that piece to look like that. And same thing for this. It's going to come down. I'm going to do something. I'm going to erase something in a second, but I just wanted to draw it. But the one thing I'm going to go back and erase is remember that we said at 1, it has a hole. So I opened that back up. And if you graph these on the calculator, it actually does show you a hole in the graph. So that's my hole at 1. So this is what that rational function looks like. So next class, we'll do the one over there on part B. And then the next video that I show you will be a little bit shorter than this, and it will just go through another graphing one with that other handout.